All right, I'll begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for these students. I just pray to be with us today. Help us to glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. All right, so before I get into the review of test number 3, I just want to spend a couple minutes talking about another way to look at the Jacobian. So I'll remind you differential forms are, the thing about differential forms is you kind of already know a little bit. For example, if x is a function of u and v, then you know the total differential of x is what? It would be like partial x partial u du plus partial x partial v dv, right? Or just to keep myself from writing so much, xu du plus xv dv. Nothing too profound there. We've done that before. And likewise, if y is a function of u and v, then dy would be partial partial y partial u du plus partial y partial v dv. In other words, y sub u du plus y sub v dv. All right. So that's just total differential. That's not even part of the recreational part of this course. That's part of the required content of this course, right? But something only a ridiculous person like myself would even consider putting into Calculus 3 would be this idea, that you can talk about the wedge product on differentials. So what's the wedge product? Talked about it a little bit before, but essentially the key features are this. du wedge dv is equal to minus dv wedge du. And du wedge du is equal to 0. That's also dv wedge dv. So it's kind of like a cross product. It's anti-symmetric, and if you do the thing with itself, it gives you back 0. But it's also not like a cross product in the sense that the output of the wedge product of two things is not a thing of the same type, right? I mean, you start with something with one differential, you're left with something that has two differentials, so it's not quite the cross product. It's like it, but it's not the same. Anyway, given this, I want to show you something. If we calculate dx wedge dy, what do we get? We get xu du plus xv dv wedged with yu du plus yv dv. So the way the wedge product works is it just, like ordinary algebra, distributes through, and you can pull scalars out. So like u with u and v with v, these are both 0. So I can ignore those, right? And so all I have is like xu times yv du wedge dv plus xv times yu dv wedge du. But then we can put these in the same, we can group these together, right? Because this, if we change the order of the u and v with the wedge product, we get a minus. And so what that gives me then is xu yv minus xv yu du wedge dv. But maybe you can recognize what this is. What is this? This is precisely partial x comma y partial u comma v. It's the Jacobian determinant, right? It's the determinant of xu yu xv yv. So the wedge product gives us a way of calculating determinants without calculating determinants. You don't have to remember cofactor expansions. You can just work it out. Here, let me try it on. Let's take it out for a. Let's try it on something a little bit more explicit. How about x is equal to r cosine theta, y is equal to r sine theta. So dx wedge dy is equal to cosine theta dr minus r sine theta d theta wedged with sine theta dr plus r cosine theta d theta, just taking the total differentials of x and y. with respect to r and theta, respectively. And what do you get? You get yourself r cosine squared theta dr wedge d theta minus r sine squared theta d theta wedge dr. Again, the dr and the d theta terms are 0, because that's how wedge products work. And when we switch the order of theta and r, what do we get? Which is r dr wedge d theta. So from this I can read that the Jacobian determinant of x comma y with respect to the variables r theta is equal to r. There's more than this, though. You see, there's something interesting and different about the wedge product. Is there's a distinction between like dx dy, dx wedge dy is equal to minus dy wedge dx, right? So it's not the same as the dx dy we see in the integration, right? There's a sense of orientation. It can tell which one came first, right? And that's also reflected in the Jacobian determinant. Because if I switch the order of x and y here, it brings a minus over here. Or if I switch the order of u and v, it changes it by a minus. So this sensitivity to ordering of parameters is built into the determinant, the wedge product calculation. We kind of make it go away in the change of variables theorem by taking the absolute value of the Jacobian, because we're not doing an oriented integral when we calculate a double integral. We're just calculating the net signed volume. When you do an integral over an area, right? It's not like I do the integral from top to bottom and then left to right, right? I mean, it's just the integral. Now you can set it up top to bottom, left to right, or vice versa, but that doesn't change the sign of it, right? It's not like I'm doing the double integral from left to right. I'm doing the double integral from right to left. That's not the concept that we've had. So there's something more in here. Now you could try to do problem, what is it, 90? I had an idea. I'm not sure it's worthwhile. Let me just play with it for just a second here. So we had like x is equal to rho cosine theta sine phi sine alpha, right? Y is equal to rho sine theta sine phi sine alpha. Z is equal to rho cosine phi sine alpha. W is equal to rho cosine alpha. So let me define this to be x bar sine alpha, y bar sine alpha, z bar sine alpha. All right, so my x bar, y bar, z bar, those are just the underlying three-dimensional Cartesian spherical coordinate formulas, right? So my thinking was, I want to calculate dx wedge dy, wedge dz, wedge dw, right? I know that when I work that out, the coefficient of, well, I don't want to write it here because I want to write something, but let me if you'll allow me this manga-style comment. We know that this is going to work out to, if you believe the math here, partial x, y, z, w, partial rho, phi, theta, alpha, d rho, wedge d phi, wedge d theta, wedge d alpha. So I'm just looking for that coefficient. The coefficient is the Jacobian. That's the thing that's a pain in this problem to calculate, right? So my thinking was, if you look at it this way, right, that's really just like dx bar. Oh, excuse me, let me write it this way. It's sine alpha dx bar, right, plus cosine alpha, plus x bar cosine alpha d alpha, wedged with sine alpha dy bar plus y bar cosine alpha d alpha. wedged with sine alpha dz bar plus cosine alpha, good grief, keep doing the same thing, plus z bar cosine alpha d alpha wedged with d rho, stupid. I try to write the coefficients first. Cosine alpha d rho minus sine alpha d alpha. And my thinking was, if I did this right, maybe I could look at it like I would get a sine alpha dx bar wedge dy bar wedge dz bar, right? Plus other stuff. But like I already know what this is from our previous calculation in class. I already know that that works out to rho squared sine phi d rho wedge d phi wedge d theta. But anyway, I haven't finished this calculation. It's just an idea. It might be a way to go through it in a different way. But I don't know, maybe you'll have just as much success just doing the 4x4 determinant straight away. I just wanted to tell you about this method of calculation. And this is another showcase of what I refer to as the method of differentials. When you pair differentials with the wedge product, it allows you to do calculations in a kind of natural way which doesn't require you to remember determinant formulas. You can just calculate, just like that. Anyway, that's all I got on that. So with that recreational math done, let's get back to your test. Do you guys have questions or homework? Yeah, let me look that up. Yeah, that is a good idea. Oh, I will eventually find my website. Come on. Mission 6 was it from last year?
Mission 6, problem 113.
Problem 113, all right. Okay, so the problem is we're supposed to find, we're going to say, let's find the centroid of the region which is inside the circle, r equals 2 sine theta. And r equals to 1 bounds some region, let's call it omega. The question then is to find the centroid of omega. So this is twist of problem 113 from last year, where problem 113 we are asked to find the center of mass and the density per unit area was y. The mass per unit area was y in that problem. The centroid, of course, assumes basically that the density is 1. All right, so first things first, we have to come to terms with what omega is. One of these things is easy, unit circle, like so, right? How do you figure out what r equals 2 sine theta looks like? So what I do, in the absence of a better idea, I convert everything to like x and y when I have a polar coordinate formula. I mean, you can just plug in values of theta and see what happens, but that can be misleading. For me, the algebraic approach is safer, so I just multiply this by r. Multiplying by r, what does that give me? R squared equals 2r sine theta. I'm like, oh, okay, well, that's good. Now I can recognize everything there in terms of its Cartesian equivalent, right? Because this is x squared plus y squared is 2y. So then I just got to complete the square, right? So I've got x squared plus y squared minus 2y. I guess I'll just add 1 here, equals to 1, right? And so that's x squared plus y minus 1 quantity squared is equal to 1. Aha! R equals 2 sine theta is nothing more than the circle centered at 1, 0. Sorry, 0, 1. And it looks like radius 1, so it's this thing, right? So what region is bounded? Omega is up in here, right? Omega's in there. Now, I'm going to need to do integrals over this region, right? So I want to come to terms with what it is. Yeah. That's exact. I need to figure out what it really is, right? So I mean that I need to figure out these points, right? I mean it's fairly clear that the inner radius is 2 sine theta, right? And the outer radius is just 1, right? Because this is 1. So if I draw a ray from the origin, maybe. Oh. Uno momento. No. Ooh. Oh. Oh. Yeah, that's unpleasant. Oh, yeah. I thank you for that. Outside. Otherwise, what I'm doing, this I'd have to break. That's unpleasant. In polar coordinates, that is an unpleasant region. So thankfully, omega was out here. Sorry about that. I failed to. This is what I get for trying to remember the problem from the computer all the way over to here. As you can see, I will lose in a game of memory every time. Let's see here. So omega's up there. So the tables have turned here. If we take a ray from the origin, we hit 1 first, and our sine theta second. So it's 1 less than or equal to r less than or equal to 2 sine theta. All right, but I still need to figure out where the purple dots are, right? So that is where 1 is equal to 2 sine theta, right? In other words, sine theta is equal to 1/2. So the symmetry of the problem, I mean, the first solution over here, this one's at pi over 6, right? And so you can see pi over 6 less than or equal to theta less than or equal to, well, this one's also pi over 6 up off the negative axis, right? So pi minus pi over 6 is, 5 pi over 6? I would argue that's the toughest part of the problem. First of all, not, interpreting the problem correctly, not making it way harder than it needs to be. So okay, so we're trying to calculate an integral over this region, basically, is what we're going to end up doing. Right? Okay. So we want to find the centroid. Now we have at least described omega. So to calculate the centroid, we need, first of all, we need the area. What is that? Right, so let's see here. For this, that's the integral from pi over 6 to 5 pi over 6. Integral from, what was it? 1 to 2 sine theta. And then we've got ourselves an r dr d theta. So what's that give us? Let's see, so that, 4 sine squared theta, thank you. So I have, now, I think from the symmetry of this problem, I could just double up what? I could take the integral from pi over 6 to pi over 2, right? By symmetry, I can say that this is the integral from pi over 6 to pi over 2 of 4 sine squared theta minus 1. See, I just got rid of the half by doubling. Is that right?
That's math.
Or did I do the opposite thing I'm supposed to? No, that's right. That's right. Twice. Sine squared theta is what? Sine squared theta, I would remind you, 1/2, 1 minus cosine 2 theta. Now I'd love to just throw away the cosine 2 theta term, but I have no such luxury here because we're not integrating over like a whole period or something. So that gives me, 2 minus 2 cosine 2 theta minus 1, so, yeah. And then I integrate theta plus, integration, minus the sine of 2 theta evaluated from pi over 6 to pi over 2. So that gives me pi over 2. Now sine of pi over 2, that gives me sine of pi, so that is 0 at the upper bound. And then I have minus parentheses pi over 6 minus the sine of pi over 3, I think, right? So I've got myself 1/2 minus 1/6 is what? 1/3? Looks like I've got pi over 3 minus the square root of 3 over 2. Oh, plus the square root of 3 over 2. So 3 minus 1 is 2/6. 2/6 is 1/3, right? Now that's not the answer, right? That's just the area. That's effectively the mass here, quote unquote. Now, by symmetry, right? The x bar is equal to 0. So the average x over the region is 0. So it remains to calculate the y coordinate for the centroid, though. So y bar is equal to 1 over the area, which I'll just say a, because I don't want to write this 30 times, right? I get no joy from writing this number 30 times in the calculation that follows, so just write it as a, 1 over a, but I don't want to forget it either, so write something. Integral over omega, but what is that integral? That integral is pi over 6 to 5 pi over 6, integral from 1 to 2 sine theta. And now we have y, which is r sine theta, and then r dr d theta. So again, what this is, just schematically, is it's 1 over the area of omega times the double integral of y dA over the region. Okay, so that's 1 over a. Integral from pi over 6 to 5 pi over 6. And then I've got sine theta. And then I've got r dr, r squared dr rather, which is what? So I get 8 sine cubed theta over 3 minus 1/3 d theta. Yeah, I could do that. So, do you follow me? Everybody follow me? So I integrated r squared to r cubed over 3, and then we evaluate from the bounds there. All right, so you say factor out of 3. I'll take that under advisement, and I'll double it. So I have 2 over 3a integral from pi over 6 to pi over 2, because again I have the symmetry, right? Of the y. I mean, I have symmetry of both the region and the integrand. Y is no different on the left and the right side of this, right? Yeah. Now, I would get into trouble if I did that for x, right? Because the x is different on the left and the right. Okay, but, and then this is what? This is 8 sine to the 4th. 8 sine to the 4th minus sine theta, d theta, right? So then we have to figure out how do you integrate sine to the 4th. Do you remember? It's going to sting a little. All right, so sine to the 4th theta d theta is the integral of sine squared theta times 1 minus cosine squared theta. Well, I guess I'm trying to remember what's the easiest way. No, I think I got to take my medicine here. This is 1/2 1 minus cosine 2 theta quantity squared. So that gives me 1/4 integral of 1 minus 2 cosine 2 theta, plus cosine squared 2 theta. See where I'm going? And then we do a half angle again on that. So I've got 1/4 integral of 1 minus 2 cosine 2 theta plus 1/2 of 1 plus cosine of not 2 theta but 4 theta d theta. And then you can integrate that, right? So this is equal to, you've got a half, you got 3 halves. We get the integral of, I think, 3/8, and then minus 1/2 cosine 2 theta plus 1/8 cosine 4 theta d theta, which of course is 3/8 theta minus 1/4 sine 2 theta plus 1/32 sine 4 theta plus a constant.
You can do eights.
Hmm?
Rub the quarter back in. Wow.
Yeah. Two over 3a. Ay. So, if you don't mind, I'm going to take care of, okay, so 8. Oh, and there's an 8 multiplying the sine to the 4th, huh? A little bit, yeah. So 8 times this goes to 3 theta minus 2 sine 2 theta plus 1/4 sine 4 theta, right? So here's an antiderivative to this term, right? What happens when I plug in pi over 2 into that? I get 3 pi over 2. The sine term, yeah, 0. Sine 4 term, what's 4 times pi over 2? Oh, 2 pi, yeah. So both the sine terms are kaput. And then how about pi over 6? So I have to subtract the pi over 6 terms minus what? Minus, put in pi over 6. Oh, so 3 pi over 6, right? I'll put some parentheses here. And then minus 2 times sine of what? 2 times pi over 6 is what? Pi over 3, right? Yeah. Plus 1/4 sine of 4 times pi over 6, which is what? 2 pi over 3. Alrighty. Close parentheses. Now all I've done so far is taking care of the 8 sine to the 4th term. Now I have to subtract the sine of pi over 2 plus the sine of pi over 6. Thank you. Indeedly. Indeedly doodly. Very good. Thank you. In fact, it should be plus cosine, right? Yeah, and then you can put in the numbers and simplify it. Yeah, don't forget the area. That's true. Tell you what. For the sake of curiosity, I'm going to go ahead and calculate that directly. So what was the integral we were doing? Integrate sine to the 4th of x. No, 8 sine to the 4th x, right? Minus sine x from x equals pi over 6 to x equals pi over 2, right? If we believe Wolfram alpha, and I think I do, the integral of the, ignoring the factor in front of the integral, we get 3 square root of 3 divided by 8 plus pi. That's what that stuff I have in parentheses up there should simplify down to. Plus pi. No, not y. Should be a number. So if I take that, right, and multiply that by what? 2 divided by 3 times the area. What was the area? We said pi over 3 plus square root of 3 divided by 2. I get about 1.321. Which makes sense. About right there. They used to have that show, Here's Your Life, right? You guys ever hear that? I don't know. I don't think it's before my time. This is like, that would be the test. Like this one problem. It's practically enough for a test. There's so much in this, my goodness. But I'm glad we did it. There's lots of good integration to see here. Now, I wouldn't be happy if a problem I gave you on the test had quite this much in it, right? But a lot of the subparts of this problem we just worked out are decent fodder for a test. Certainly, I do want you to be able to integrate powers of sine and cosine. So don't leave yourself open to like not know how to integrate cosine to the fourth or sine to the fourth or something like that, because it might happen. You never know. What? Calc 2 is a prerequisite for a reason. Yes, sir.
That's awfully similar to the problem on the homework. Except, no, well, but the difference is the problem in the homework, aren't you calculating that middle part instead of, you're calculating the intersection, not.
Oh.
And the circle, well, the circles over there. Well, yeah, the radii are different, but you're calculating the intersection. It's cosine instead of sine, and it's the radii. And calculating.
Oh.
Don't do that after we've worked on this question for hours on end. Don't look at it.
Well,
Can you just change it so it's like on one side and
Easier.
the other side instead of like what's in the middle?
but people have already been working on it, yes? Have you figured it out yet?
No.
Ah, then we should think about it. I mean, there is partial credit. I just think it's not good to just give up on something because it's difficult. Right? We should. So your problem is, what is it?
R equals 4 cosine.
This one. So it's centered at 2, 0. And the unit circle?
And the unit circle went 2.
Oh, the two circle. Okay. And what you're supposed to do? What?
And it was bounded by both of them.
Yeah, I admit that language is not entirely. I mean, there's different ways you could read that. You could read it as just both of the circles put together. You could read it as this region. You could read it as this region, or you could read it as that region. So if you'd like to, for the homework, you're welcome to read it as this is the region which is bounded. Which would be way easier, right? Because then you have a clear inner and outer radius, right? For that. Yeah, but if you want to do the overlapping region, I'll also allow you to do that. Sure. Let me well, let me try to look at that for just a second here. Try to see if I can't think through it. So for the let's face the difficulty here. So this is what? This is 2, 0. All right, so the problem with this in here is if I start from the origin, right, and I draw rays like this, well, for the brown, for all these, right, I certainly have 0 less than or equal to r. Oh, forget this. I have 0 less than or equal to r less than or equal to 2, right? Because this is 2. But you can see, even with the poor quality of my picture here, that you're missing something. You're missing this little sliver in here, and like this little sliver in here, right?
Where r is only bounded by 4 cosine.
Yes. That was amazing. I'm sorry.
Like I had
That was funny. Sorry. Yes.
You allowed us to use symmetry on the first problem to determine that x is equal to 0.
Yeah.
We use symmetry on this problem to determine the coordinates just by looking at it. I mean, it's going to be at 0 or 1, 0 just by looking at it. If it's bounded. Sorry, I think geometrically it's 1.
Oh.
We could do calculus.
Oh. You might have me there. That's also true of most of the nicest, any of the optimization problems I'd like to give you on the test. If I allow you symmetry solutions, all of a sudden there's no calculus to do it, right? Like, maximize the volume bounded by a certain amount of material to make a box.
Unless you
It
say
will be a cube. What's that?
Unless you say it would show me.
Oh, use calculus. I know. It seems so heavy-handed, though, doesn't it? Let's see here. So let's see here. I need to make it larger. So, like, from here to here, well, wait a minute. You know what? There's no mystery. There's no mystery at all. Timothy was Tim. You don't say. You go by Tim or Timothy, either one. But I mean, I was thinking, oh, you need 2 different functions. No, this is all just r is equal to 4 cosine theta. There's no. It's just there's just 3 cases. So you have this. Not even that word. All right. So case 1, case. You have the case 0 less than or equal to r less than or equal to 2. Is that 45 degrees? Where is that? Where do they intersect?
It's plus or minus
Pi over 3. Okay, so this is for minus pi over 3 less than or equal to theta less than or equal to pi over 3 if I trust you guys, and I do. That's case 1, let's say. And then there's case 2 and case 3, which is 0 less than or equal to r less than or equal to 4 cosine theta, right? And that would be for like pi over 3 less than theta less than pi over 2, yeah? case 3, minus pi over 2. Oh yeah, multiply it by 2 is a great idea. Although I guess if we're going to go that path, maybe we should take Luke up on his offer to do no calculus. But that would be case 3. You'd have to break it into 3, at least distinct regions, and then. But symmetry helps us out. It lets us multiply one of the little slivers by 2 to get the other one. Yeah, but there's plenty to. I mean, calculus here. There's a lot of things going on, a lot of moving pieces. Your basic idea of setup is right, though. And sorry, I really did mean for this problem. I think I meant for this problem to be this originally, but I need to be more clear in my wording. If I do something like this on the test, you should talk to me. Like, don't automatically assume it should be the worst possible region bounded. You should say, you meant this one, right? And I will be glad to tell you, yes, please, that one. You know.
Your wording was literally find the centroid of the region bounded by these two things.
Right. My wording is dangerous. Take a communication class. I did take one once upon a time. It did not help. Okay, give me a second here. Now both the circles. Then the question is, how do you consider the overlap, right? If it's a centroid, I think you have to make sure you don't double count the overlap, right? But if it was two disks that were overlapping, then you would count the overlap. I mean, if it was actually center mass problem.
Would you have to change the boundaries to equalities or something?
I mean, if I had a bunch of quarters, right, just lying on a table, and some of them were overlapping a little bit, I would just use the centers of each quarters and just add them, and treat them as point masses at the center of each quarter. But I think I'm talking about physics now, so let me get back on track here. Don't want that. Just give me just a minute or two here, guys, and then I'll let you go. The test is next Tuesday, right? So I wanted to remind you that, come on. Well, let's not look at the solution. That's too cluttered. So I think we already did this on the last test, so I don't see myself doing that on your test, right? Because we did that last test. Calculate the gradient in non-Cartesian coordinates. That already happened in here. Critical point, find multivariate power series expansion. That looks peachy keen. That looks like a reasonable problem. Oops, what happened here? Find all critical points of this function. That looks good. Extreme values on a disk. Right up our alley. Min-max saddle. You're given a power series. Interpret. Nice problem. Requires very little calculation. Completely tests whether or not you understand without any additional calculation, really. The point of this calculation is that you can't do it unless you switch the bounds. So this is a switch bounds and integrate problem. Here's just another switching the bounds. So I'm really testing, do you understand how to reformulate xy versus yx type integrals? We've done a lot of that. Triple integral over a solid cylinder of radius 3 for 0 less than 3, z less than 1. This is okay, so you should use cylindrical coordinates, right? 0 to 3 for r, 0 to 2 pi for theta. Z goes from 0 to 1. X squared plus y squared is what in terms of cylindrical coordinates? R squared, all right. This one, we're looking at the solid sphere of radius 2. in the positive z. I mean, z is non-negative, right? So here you'd let theta sweep from 0 to 2 pi. The phi would go from 0 to pi over 2 because you go down to the xy plane, but that's it. And you'd use spherical coordinates here. How do you convert x squared plus y squared to spherical coordinates? It's r squared, and r is rho sine phi, right? So it's rho squared sine squared phi, and then you still got your rho squared sine phi, d rho, d phi, d theta. Oh, one of these. Ugh. Hey, but it's a box, so it's not as bad as what we were just doing, right? Find the area of the elliptical region. Hey, I worked that the other day. That was one of our first change of variables examples. I am fond of this problem. That was quiz 3. Test 3. Again, I don't see problem 1 happening on your test 3 because we already did that last test. But looking at it, I think the rest of them... Ooh, a ninja. And an eagle. And a fence. Ooh, interesting. Ooh, forced calculus, because you could do argument by symmetry. Here's a center of mass problem. Change the order of integration problem. Change to polar coordinates problem. Change to spherical coordinates problem. The volume of the ellipsoid. See, I put the area of the ellipse on the quiz. I put the volume of the ellipsoid on the test. That's mean. That's. Oh, look, one of these. Oh, I do expect you to know how to do those too. Convert from the messy bounds to. How would you do that? Basically, the point here is that is the sphere of radius 2 above the xy plane. If you study these bounds, you can see that's what it is. So you can convert to spherical coordinates and do the integral. Here's one like the example we worked out yesterday with the linear change of variables. But anyway, the solution to these, of course, is posted, so you can look at it, and we can talk about. I'll probably mostly talk about the solution to the homework you guys are working on Monday, but also these old quizzes and tests if you want to. But that's what the test is probably something like 40% optimization power series, 60% integration, something like that. Thanks, guys. Have a good weekend.